Okay, let's start again. So now we have Mikel Sanchez-Garitaonandia. He's talking about the megahertz gravitational waves from neutron star mergers.
Yeah, so let me start by thanking the organizers, of course, for giving me the opportunity to present this work. And I have to say that I come a bit from the outside of this field, so please don't be shy with questions nor comments. I'm really excited to hear your feedback. And I would like to present you about the possibility of having a new source in the megahertz band that would come from neutron star mergers. And I would like to go a bit into details of explaining this. So as you all know and are familiar with, it's been a while since we know QCD, at least what it is Lagrangian. And it has been a complete success inside the standard model. But we know that there's several features of it, very important, that remain unknown. This, as you know, is due to the fact that this is a theory that becomes strongly coupled at the relevant scale, the microscopic scale, where a lot of fun physics is supposed to happen. For example, something I'm very interested in is to try to understand what would be the phase diagram of this theory. What kind of phases can we find? So this is what we have as conjecture QCD diagram, or at least part of it, in the plane temperature and net baryon density. And here, as you know, our universe nowadays, we're at very low temperatures, very low densities, and what we find is just matter confined inside neutrons and protons. So we have hadronic matter. But we know by perturbative methods in QCD that at very high temperatures, we have to find these degrees of freedom deconfined outside these hadrons. And the relevant question is to know how we go from one to the other. So what do we know so far? As long as we are at very low baryon density, we have theoretical tools that work. I'm talking about lattice QCD, which is non-perturbative. And with this, we discovered that the phase transition from hadronic to quark-gluon plasma, or quark degrees of quark matter, it's a crossover, so there's no actually phase transition. However, if we want to start learning what happens at higher baryon densities, lattice QCD starts struggling because of the same problem, and theoretical tools are quite limited for the moment. But there is a very extensive program of experiments that try to probe all this area of the phase diagram. In the first place, we have the famous heavy ion collisions that will try to probe the system at moderate chemical potentials, in particular, trying to find the suspected critical point, second order phase transition, that should happen somewhere at finite chemical potential. From this critical point, it's expected that a first order phase transition arises. And if we want to probe the system at much colder temperatures and high densities, we would be in a regime where, as far as I know, there's no experiment in Earth so far, but we have systems out there that fall basically in this region of conditions, and that would be neutron stars. And that's basically gives the context for this talk. So what do we know about neutron stars? Or what can we learn about QCD from neutron stars? By simply looking at neutron stars that live isolated and looking at how the mass depends on the radius of these stars, we can start putting constraints on how stiff is this matter in those conditions. In other words, what is the phase, the equation of state, at very low temperatures, or how the pressure relates to the energy density inside these stars. And thanks to that, there has been several results. And combining theory constraints coming from what we know at very low densities from nuclear theory and at very high densities from perturbative QCD, what we have done is restrict a lot what is the availability or what is the possibility of the equation of state of QCD. So in this way, we can learn a lot about what happens at very low temperatures and high densities. Furthermore, it's very exciting that we measured in 2017 for the first time the merging of two neutron stars, because this implies that now we can detect gravitational waves that comes from systems that are very dense, but they are not at so low temperatures anymore. They heat up a bit because of the merging. And therefore, we can have access not just to the very low temperature part of the phase diagram of QCD, but hopefully to a region a bit extended. So in this context, there has been a huge effort in doing simulations that try to predict what kind of signal we can obtain from such mergers. And in particular, I'm going to refer to a simulation that was done last year, in which the simulation was done by coupling a neutron star described as a perfect fluid, couple this to general relativity, and we just let the system of two neutron stars merge with each other. So the model that was used in this simulation to describe the matter was some holographic model that, for the purpose of this talk, the only thing that I want you to know is that it was a model that could be tuned to fall within the constraints that we know for the equation of a state at 0 temperature. And furthermore, one can then extend it to finite temperature. And of course, it's just a model, but we can try to get some intuition of what would happen in a model like that with phase transitions in the phase diagram.
Sorry. What was the microphysics? Were you including neutrinos and things like this?
In these simulations, no. Weak processes were not present. Yeah. So in this...
Wait, without weak processes, is that realistic? Because that's the main cooling channel.
It's realistic to some extent, but of course, one has to try to incorporate that, and there's an effort by the same group, as far as I know, in which they're trying to obtain what would be the effective viscosity that comes from weak processes.
Maybe the answer is, I see they only went out to 5 milliseconds. By that time, neutrinos would still be trapped, so they wouldn't be an effective cooling channel, perhaps.
They are radiation pressure.
Excuse me?
Add the radiation pressure.
Yes. In principle, they have to
true,
be added. This is a first step, if you want. And actually,
Okay.
one could argue if in these scales, it could be that they are not extremely important, but as you say, they will add for sure. And there's efforts actually to try to incorporate viscosity, an effective viscosity that comes from these interactions into the simulations. But of course, there's complications with viscosity and hydrodynamics. But there's an effort on that direction, of course. So this is a first step. Let's take it like that. And the goal would be, of course, to incorporate all of those processes. So here what you see is 3 snapshots, which are the different columns. And what they are representing is the net baryon density that you find in the star, in the merger. These are time snapshots after the merger, so you only see the blob that has been as a consequence of the collision. Then in the middle row, what you have is the temperature in MeV, and then down here you have, and this is important for this talk, is the fraction of quark matter that has been formed according to their model. And you can see that there's some contours drawn here of size of the order of kilometers, which means, or what they represent is that inside these contours, the matter properties are such that there has been a phase transition, and therefore I start producing quark matter inside these spots. And they are of size quite considerable. So some remarks about the simulations. As you see, the characteristic time scale, as you probably know, is the millisecond, which gives rise to signal in the kilohertz. And let me emphasize that this is, let me call it the macroscopic time of the simulation, of the process, and it's extremely large compared to the characteristic time of QCD processes. Furthermore, the regions in which this phase transition is happening, it's of size of the order of kilometers. If I am very, very optimistic, I take this 5-kilometer blob. But it's of the order of kilometers, as you see, which is massive compared to the femtometer, which is the characteristic size. So from the process of QCD, all of this is happening, let's say, at each cell at infinite volume and in a very adiabatic and careful way. So something that was not discussed in these simulations, and I want to raise the question, is what is the dynamics of formation of this quark matter inside these neutron stars? And for those that are familiar with the cosmological phase transition story, there's going to be a very strong parallelism, given that in that case there was also a very adiabatic evolution of the universe. And the only thing that you have to think of is of replacing the macroscopic rate, which would be the Hubble time, by the millisecond in this case, and the critical temperature at which the phase transition would happen in those scenarios, with some a bit more complicated energy scale that would come as a combination of temperature and now chemical potential. So what do I mean that the dynamics of this phase transition, or the realization of this phase transition, has not been considered dynamically? Is that in practice, very schematically, what is done in these simulations is that we have some phase diagram according to our model, and different patches of the star start in some hadronic matter. They have some evolution in the phase diagram, and when they hit a first-order phase transition line, we just claim that there's a switch in what equation of state we use to describe this matter, and now we change to this green line, which would be characterized by a different equation of state. In practice, we know that phase transitions, when we overcool or overheat and overcompress, in this case matter, very carefully, what happens is that our hadronic matter would go a little bit beyond this critical line, and it would enter a family of metastable states. So it would be trapped in some false minima of an effective potential. And then when it gets deep enough and it takes long enough in those states, there would be a tunneling process that would make it fall into the preferred phase in those conditions. And then we can shift or switch into the new equation of state and continue our evolution. So what I'm going to focus in this talk is about that process of tunneling, and see that there might be an extra source of gravitational waves coming from it that would be in a different band of frequencies. So pictorially, the process is the process of the phase transition is represented here, where I took it from some lattice hydrodynamic simulations in the context of cosmological phase transitions. So at early times, what you see is that we have some metastable phase filling all of our parts of the star, and then the preferred phase nucleates in form of bubbles at different places. Because it is the preferred phase, these bubbles would expand because they have greater pressure inside, and they would start eating the rest of the metastable phase. But at some point, they will start encountering each other, colliding with each other, and at late times, when the walls of these bubbles basically have mostly disappeared, and if I go beyond in the simulation, they would fully disappear, what I'm left with is with the preferred phase at those conditions, but highly perturbed. And it is these perturbations that I will show that they are of very long wavelength compared to the microscopic scale that will live very long enough, or they will live very long, and hopefully long enough as to produce enough gravitational waves that could be detected nowadays.
What's the scale?
The scale, it's a few units of, it's some few units of the thermal scale in the simulations. Yeah, that we can discuss a lot about this if you want, about how. Sorry?
Is that comparable to the scales you had?
No. That's, let's say, subtleties that are in the lattice simulations that we could discuss much more in detail if you want, but I don't want to get into right now. Yeah. Yes, that's the tool they use. They start increasing the size of the box, this time of simulations, and try to find scaling properties. Yeah, because at the end, you need to be able of resolving somehow two very separated scales. So this is tricky. Yeah.
But
yeah.
At this stage, now you're not considering at all the model that you were using when you were.
No, with this is a simulation done by other people. I just wanted to show what is the picture we have to have in mind as happening inside these patches in the neutron star. I still didn't go to.
It's just standard bubble nucleation.
Exactly. Just a standard bubble nucleation. Yeah. So why should I care about this? As you probably know, first order phase transitions, or phase transitions in general, should be a property that happens at very microscopic lengths and times. But however, they have very long lasting effects, actually macroscopic effects. And the one in charge of doing that is that there is a big suppression of nucleating bubbles. And as you see here, this is the probability of nucleating a bubble per unit time and volume. This goes at some microscopic rate, so it would be very fast compared to the macroscopic scale, but we have a very large suppression given by what is the energy of the fluctuation that my system needs to nucleate a critical bubble, which is the minimal bubble that would start expanding and could really fulfill the phase transition. So the key is going to be to try to estimate this in our case. So for the purpose of this talk, now I emphasize that I am not assuming any specific model. That the only thing that we have to have in mind is that we assume that there's an existing first-order phase transition in the QCT phase diagram, and that is going to be accessed during the merger. And then I need to try to get some estimation to what is going to be the typical energy scale at which this phase transition would happen, and let me take a value of this order, which is more or less what we find in the phase diagram. So the outline is I'm going to try to get a peak frequency of what would be the signal of gravitational waves coming from this bubble nucleation story, and try to convince you that this is quite robust, that it's going to fall in around the megahertz. Then I'm going to give you a very raw estimate of what could be the peak strain, and this is very preliminary. There's work to do here. And finally, let me conclude and what kind of things I think we should do in order to improve this computation. Any questions so far? Okay. So let me give a very simple argument, which probably some of you are familiar with, is that if I now consider a patch of a star of a size, optimistically, of 5 kilometers, but you can put here a few kilometers for what I'm going to tell now, if I have any hope that the phase transition would happen, I need that at least in a microscopic time, in a millisecond, at least I'm going to nucleate a single bubble in this whole volume. So the expected number of bubbles is going to be basically the nucleation rate per unit time of volume multiplied by the volume and the time of the millisecond. And I need to have at least one bubble in this time and in this volume. And from there, I could get an estimation to what is the energy of this fluctuation that I need, what is the action. Yes?
Why isn't it spherical?
Why isn't it spherical? Because the symmetry, there's no spherical symmetry in the merger, right? You have these two spheres that collide with each other, and then inside anything can happen. Yeah. It is true that at late times, by the calibration of the star, if some part gets overcompressed, that would be more similar to a spherical spot. Yeah.
Saying you were in equilibrium, so very fast structures will tend to make it spherical. What's in a small time scale?
But maybe not such a short timescale, because the timescale for this to become spherical is basically the size of the neutron star, whereas the phase transition happens faster than that.
Yeah, that's a macroscopic
In the
effect.
analogy with cosmology, the size of the neutron star is Hubble, and the
Yeah.
phase transition completes in less than a Hubble time. But I think for his signal, that's not important, because the signal, after all, is generated at the microscopic scale. So the macroscopic shape of this region will not affect the gravitational wave signal to the lowest order, probably.
Actually, that brings me to my next point, and is that it's a bit weird that this volume is here, because this is a microscopic effect. So this is a very intuitive argument, but it's slightly wrong. But I like to present it better like this. If you go to the paper, the more accurate description tells you that instead of this volume, you need to take this other volume, which is the volume that a single bubble would cover in a millisecond, expanding at some velocity given by VW. Okay? So to get to this formula, which resembles a lot the previous one, it's a bit more obscure. That's why I wanted to avoid it. But we could go into details if you are interested. And then it doesn't really matter the geometry of anything. This is something that happens at microscopic scales. So I could now get a value for this if I plug my assumption here, and then I have to assume something where big errors can start coming, which is at what speed do these bubbles expand? And knowing this is hard for weakly coupled theories, for strongly coupled, even more. But what I'm interested in actually is not the value of this action, but what it can allow me to compute, which is what is the time in which this phase transition would take place. And that is given by the derivative in time of that exponent that is here, that action. And the intuition is very simple, and it's simply that if this derivative is very large, nucleation is very enhanced fast in time, and therefore my phase transition would happen almost immediately. If this derivative is very small, it means that I need a lot of time for nucleation probability to be enhanced enough as to have a phase transition. So an estimate of this would be to compare the two scales we have for S and the time, which would be like this, and it gives us something of the order of the microsecond. So it's 3 orders of magnitudes below the macroscopic scale. And for those of you familiar with the numbers that showed up in electroweak-like phase transitions, this beta over the Hubble rate is also of similar order, which I think is a funny coincidence. So in these 6 microseconds, what happens is that we start nucleating bubbles. They grow to macroscopic sizes characterized by this big R, which is the average distance between bubbles at the time of collisions. Then they all disappear, and they leave behind this preferred state that has very long wavelength perturbations. And because they are very long wavelength, viscosity is very damped, it's very suppressed, and we expect them to live for a macroscopic time of the order of a millisecond. And this, in principle, could hopefully build up enough emission as to be detected. Hopefully. So in order to estimate this size, which would give us the characteristic frequency of our signal, it's simply how big they became. So what is their speed of expansion times the time that they had to expand, the time that the phase transition takes place. And from there, I can get just the frequency as this ratio. And with the values that I mentioned that I was going to take as ballpark, I get something very close to the megahertz. And let me stop here for a second, because you see that there's many quantities here inside the logarithm. So this logarithm protects us from making big mistakes in the order of magnitude of this frequency, as long as we are not at very, very small wall speeds. And if we take here the value of a speed to be 1, which would correspond to the smallest frequency, it gives us something that is still of the order of hundreds of kilohertz. And then, of course, if I have an extremely tiny wall speed, this could go to very, very high frequencies, but would also kill the signal completely because the average speeds in the system are going to be killed. Yes?
So what is the relation with the speed of sound in that system? So are they supersonic?
The wall speeds?
The wall speeds.
I didn't assume anything about that for the moment. And for this computation, you don't need to know that.
For the gravitational waves, it will be crucial, no?
It will, but for the computation of the peak frequency, no. But for what is the strain that you get, yes, because it changes a lot of the profile of these bubbles expanding. You're right. Yes, there's a question there behind.
Thank you. So I think, okay, V wall, fine, but the point is that 10 to the minus 3 megahertz, right? So this, where it is 1 over tau that gives you this 10 to the minus 3 megahertz?
So this 10 to the minus 3 megahertz comes from, comes from the fact that we have a millisecond. So the frequency is this ratio that is dimensionless divided by the characteristic macroscopic
Indeed. So
time.
Basically here you're just saying that whatever the dynamics of the bubble, the frequency of the gravitational waves is determined by the duration of the merger.
No,
the
I mean,
millisecond, right? That's
millisecond,
what gives you the megahertz.
The millisecond gives you what is the macroscopic time, and therefore from there you derive everything. Yes, of course. But if you want, what it seems robust is that your phase transition will happen 3 orders of magnitude below that millisecond, or below the macroscopic time you want to take.
Okay, and so in this formula, the 3 orders of magnitude comes from this prefactor, logarithm over V wall, etc.?
No, this 10 to the minus 3 megahertz comes from the fact that what gives you units to this frequency, it's 1 over tau, this tau that I said, the macroscopic time scale. So it's 1 over millisecond.
So, or it is, either it is 1 over tau or it is some factor over tau. So that's what we are asking.
Okay, I'm dropping that factor.
So basically you could have no phase transition inside at all, and you could just say, okay, the merger creates gravitational waves and they are going to be at the megahertz, right?
Why do you say that there
because
wouldn't be a
it's
phase
1
transition?
over tau.
1 over tau is a kilohertz.
Yeah.
1 over tau is a kilohertz, not a megahertz.
So he's not dropping the factor.
Yeah. So
If he has the megahertz.
I'm dropping a possible. I don't know if I'm understanding well.
the two of you are confusing each other.
Okay.
Probably
because
let's move that for the
10 to the
discussion
minus 3
session.
megahertz is a kilohertz. That's tau.
Yes.
Or that's 1 over
yes, 1
tau.
over tau. Yeah.
But you're keeping a factor of 1,000 that takes you from that to 1 megahertz.
Yes.
And what Chiara is asking is that factor of 1,000 the logarithm and the 8 pi and the VW? And I think the answer is yes.
The answer is yes. Sorry. I didn't understand.
Thank you.
Yes. By giving the values of lambda tau that I assumed and the wall speed of 0.1, this quantity takes you from 10 to the minus 3 to 0.6. Sorry for the misunderstanding. 5 minutes. Oh, Jesus. Sorry. Okay, so I hope that I convince you a bit that it's going to be around the megahertz. And then let me try to make this very raw estimate of the gravitational wave strain. And for that, I'm going to borrow a heuristic formula that comes from a lot of effort doing lattice hydrodynamic simulations in early universe phase transitions. And it's quite intuitive. So the gravitational wave energy depends on some energy stored in a fluid motion. It has some building up time, which is the light crossing time. There is a characteristic wavelength, which is the size of these bubbles at the time of collision. And then there's an efficiency factor that, for the purpose of not being too optimistic and conservative, I'm going to take it to what is taken in the literature in these simulations that you can see, for example, here. That is of the order of 10 to the minus 2. Yes?
Can you quickly say why delta t is now the...
Light crossing time, yeah.
Why is it the light crossing time and not the time it takes a bubble to expand, for instance?
So this is because the gravitational wave signal is dominated by the perturbations are left behind after the walls, all the bubbles collide. And therefore, so for the purpose of these perturbations building up the signal, the expansion of the bubbles don't mean anything. And there's two things that could happen. Either is the light crossing time, because then my radiation escapes, or is the macroscopic time that these perturbations will leave. So I have to take the minimum.
It could be the sound crossing time, for instance. Or are we assuming that the speed of sound?
But the sound crossing time is bigger than the light crossing time.
Yes.
Yes. So it is true that the sound crossing time would give me a better estimate if I had an infinite volume. But the problem is that here, if I have emission from one point, in the moment that this gravitational wave leaves the spot, will not interfere with whatever is generated afterwards. So this, it's a smaller time scale, but it's simply because I have a finite volume at the end.
Thanks.
Yeah, no problem. So the strain goes like this, has the inverse of the distance, as you know, scales with the volume of this system, and then there's some uncertainty here in what is the energy deposited in these perturbations and fluid motion. And for me, the most uncertainty comes from here, which is what is the typical velocity of this system? Or, if you want, from all the energy released, which is lambda to the 4, what fraction actually goes into fluid motion? So by plugging all the numbers but, let's say, that factor, I get something like this. So in the order of the distance of 100 megaparsecs where this merger happens, if I am very optimistic in what is this fluid velocity average, it's, let's say, close to 1, so almost all the energy of the phase transition goes into the motion of the fluid, I get something of the order of 10 to the minus 24. Questions before I conclude? Or I should conclude, okay. So I hope I convince you that there's a signal, possible signal in the megahertz, for sure disconnected from the rest of the bulk of the signal that comes in the few kilohertz. This would be preceded by a very long spiral, as you already well know, in the kilohertz band. And let me say that in the same way that there would be a signal because I'm overcompressing and overheating spots in the stars, when this star relaxes, or this spot relaxes back, there could be another signal coming from the inverse phase transition. And it should happen at a similar scale because the scale of the phase transition would be equivalent. This would be an incoherent signal localized in the sky and would have a duration of the order of milliseconds. And there could be that there's several signals coming from mergers depending on their distance, my sensitivity, etc. So this requires a bit of a more careful study, of course, also the population of mergers. And finally, what do I think that we should try to put our effort in is to try to understand a bit better this kind of bubbles, which are overheated instead of overcooled, like in the cosmological case, in dense mediums and strongly coupled. And in particular, can we say a bit more about this wall velocity in these mediums? We need a better understanding of our estimation of what is the energy budget, how much of this energy in the phase transition that is released truly goes to the motion of these sound waves. Confirm that, as in the cosmological case, this spectrum would be a power broken law with specific powers peaked at the frequency I set, that this still applies here. And then there's a possibility that there's neutrino emission by the fact that this spot may fall off beta equilibrium, out of beta equilibrium because of the phase transition. And then this would change my estimation, of course. But it could have big implications in memory effects at low frequencies, as I discussed with Diego this week. And that's basically it. I'm welcoming any comments and questions. Yeah.
Thank you, Mikel. So I'm sure there are questions.
Yes, I'm in the back corner. So a first-order phase transition can complete by bubble nucleation, as you described, but it doesn't have to. It can go by spinodal decomposition also, where basically if you go through the transition fast enough, you before any nucleation happens, you get to a point where the wrong phase becomes classically unstable, and then you get spinodal decomposition.
Yes.
So that changes the microscopic dynamics, but I'm not sure whether it changes the length scales. Not at the level of quantitative predictions for strain, but at the level of length scales and time scales. Is it different from what you did? How different is it? Do you know?
So the length scale there would be set by what is the fastest unstable mode.
Right.
That one depends on the speed of sound of the medium, which it's imaginary now because I have a sound instability. And In principle, there could be a difference because I'm not sure that scale can become very macroscopic. I may be wrong here.
So you need the distance between bubbles
Yes.
is macroscopic compared to a Fermi,
Yes, indeed.
and you needed that.
For this frequency peak, yes.
Okay, so then you won't get you won't get that. So you'll get the QCD dynamics might not be so different, but you will not get this length scale which is intermediate between a Fermi and a kilometer, which
I would
comes
say,
from the
yeah.
space between bubbles. So it might actually be quite different.
I would say that it would be much, much higher. But this is a naive first answer.
So if people want gigahertz, that might be a way to get it.
That could be a way of getting it.
Although the magnitude might be uninteresting, I don't know.
Could be interesting.
It could be uninteresting. It might be very small.
I have no order of estimation of the order of magnitude of that. What I know is that then the rates, the macroscopic rate, should be quite fast in order to make QCD really go into this spinodal instability region.
Or you
right?
need a weak first-order phase transition.
Or you need a weak first order.
You either need a very fast passage or you need a weak first-order phase transition.
Yeah.
And weak first-order phase transition is not a crazy speculation. So.
It could be that also, so in theories with a large number of degrees of freedom, a jump in the phase transition, there's also a big suppression of the bubble nucleation, so that could help maybe.
Anyway, it seems worth investigating that in addition to this. And thank you for the talk. This was really interesting. Thank you.
Thanks for the question.
Okay.
So yeah, really thanks for this talk. I think this is really, really important to this community because this is the first time we are talking about a standard model signal that is not too far below the experimental sensitivities. Speaking of which, I think a very interesting aspect to this is that we would have a coincidence between the regular neutron star in spiral signal and that signal. So I think there's two things we should think about. One is cross-triggering between LVK and detectors like ours, because we've heard in Kaliro's talk, for instance, that collecting a terabyte of data a day gets challenging very quickly. But on the other hand, if you know exactly when to look, so you buffer your data for maybe the few seconds it takes, you get your live trigger from LVK, and then you decide whether you store the data or you throw it away. Also, if you know exactly when you're looking for a signal, you have no look elsewhere effect anymore, so it gets easier to dig the signal out of the noise, which might boost the sensitivity to that kind of signal. So I think this is something that is definitely worth exploring.
Happy to hear that.
Very good, Juan.
Let's talk about energetics. I like very much this talk. So a kilonova, it's 1,000 times a nova. A hypernova could be billions of times a nova. Now, in terms of energy stored in the problem, it's much more brilliant, no? A hypernova than a kilonova. Of course, there are not so many around, so it's going to be difficult. But I would guess that this kind of phenomenon, if it happens when you have two neutron stars colliding, it will also happen at the formation of the neutron star itself at the first place, from a hypernova. So it could be that you have this kind of emission, and talking about coincidence, you could do multi-messenger. So you see a hypernova flying out, and you could measure the gravitational waves if it actually came from there. Not with LIGO Virgo, which is in a kilohertz or 100 hertz. Maybe there the amplitude is not large enough. But if you go to the higher megahertz to gigahertz and you do coincidence, you might see.
It could be. This is something that is on our desk too, that I didn't mention, to try to see if in the formation of neutron stars there could happen something like this, right? At the end, there's the assumption that there's a phase transition first order being accessed. That's the key point. That could happen, indeed. That could happen. Yeah.
Yeah, thanks for a very nice talk. I was wondering if you have any idea what the signal would look like, say, in the time domain. I mean, is it completely, or in any domain, right? I mean, is it a completely because you say the duration is like millisecond, right? And that at the megahertz, right? Yeah. So it's not kind of just a single burst, right? It's kind of an extended burst. Is that how I should imagine it? I don't even know how to think about it.
In the real-time domain, I'm not sure how I should imagine it. From the point of view of the frequency, the first naive thing I can say, and maybe someone in the audience knows more about this than me, that maybe I could expect something similar to in the cosmological phase transition case. If this process is dominated, the emission is dominated by sound waves, for example, we know there that we have a broken power law peaked at the frequency that I said, and then there's a specific slopes on the frequency. Which now I don't remember much their actual numbers.
The difference there is that we're looking for a stochastic background coming from everywhere in the sky, right? You have kind of inside the neutron star the same process, right? But now it's localized in the sky,
It's
right?
localized in the sky.
So that means it's a different. I mean, then how the signal arrives by Earth, right? Should look.
But it's, let's say that in the same spot, you have several different frequencies of the sound waves around this peak interfering with each other. So I think that you get something coherent.
Okay, so you think something, what you're imagining is kind of like a stochastic background, but only lasting for a millisecond and only coming from one direction in the sky.
I would say so.
Question?
Yeah, I think you will also have the stochastic background because, I mean, you know, the neutron star mergers give you a background, so the rates are not so low. So you will have also the accumulation of all these mergers gives you something in the megahertz. Yeah.
Yeah.
Maybe the signature will be lower.
Will be lower. Okay.
Has anybody estimated that?
No.
Question over there?
Thank you. So yes, so it is a bit related to what Valerie was saying. So in the formulas you have used, that you have imported from the simulations, there are assumptions which are made, and the assumption is that the signal comes from a source which is stationary and basically homogeneous and isotropic. Okay, so clearly these assumptions are made with respect to the typical size or time of your system. So I think in this case it would be absolutely necessary, before you confirm that it is the same signal as in for first order phase transition in the early universe, that this assumption makes sense, right? So for example, that factor that you said, in which you set the light crossing time, h times, r times whatever, you have it linear.
Yes.
If the source cannot be stationary, this factor becomes to the factor squared. And the light crossing time can become, as Joachim was saying, the sound crossing time. And this obviously, it changes a lot the amplitude, right?
I agree.
So I think this is great what you had. I think one needs just to check exactly whether these kind of formulas that we have been developing in the early universe actually, they make complete sense. It is related to what Valerie was saying. I would say if you have a sufficient number of bubbles nucleated, then yes. But if you have just a few bubbles, then it becomes trickier.
Yeah, so as I said, this was a very raw estimate. And it was a first estimate, assuming that, of course, in all these paths, it's homogeneous and isotropic. Of course, there's actually gradients of properties here because we are dealing with a spot that is of the order of the kilometer, right? So then we need to start correcting this, as you say, yeah. But this was, let's say, our very first preliminary raw estimate of what can I say right now? Let's say in an easy way, in a back-on-the-envelope estimate to see if it's worth pursuing or I want to drop, let's say.
Please.
Yeah, thanks a lot. This was extremely interesting. So one thing is, so Juan stole a point that I had, which is also thinking about in terms of multi-messenger, right? Mm-hmm. Because now you cannot think not only of LIGO, Virgo, whatever, but you can also think of just observations with telescopes. Yeah. And specifically for binary neutron star mergers, you have these kilonova signals. So you have production of heavy elements and whatever kilonova spectrum. So there are a lot, actually, it's a lot of different types of signal. And since here you're triggering a phase transition, you're in principle changing all of these dynamics. So you're changing the production of elements and all of this. So I was wondering if you thought about
so I didn't think it in that specific version. What I thought for sure is if this would change in any manner, the merger simulation, because now I'm claiming that instead of having the same exact fluid with the new equation of a state, I have these perturbations that live for the order of the millisecond, which is something that it's resolved. It's the macroscopic time, so it should be somehow included in the simulations. And that, I guess it would depend on actually how much energy released has been stored in these perturbations, if it can truly alter the dynamics of the rest of the star. This is something that we have to go back to. But in the case you're mentioning me, I didn't think about it.
So precisely on this, maybe a bit on the point that was raised earlier. So is there a way of putting this prediction into a simulation? So some equation of state which looks like this, putting into a simulation and seeing if, in a real simulation, you actually get something like this?
so we thought about this and the fact of simulating at the same time. I don't know if you're going in this direction, but the bubble nucleation expansion with the rest of the merger that includes 2 different timescales is extremely hard.
I mean something which naturally triggers.
Yeah. So what we thought is about doing simple scenarios in which this could be triggered, as you say, and then try to make an estimation on. Let me now exchange when a phase transition happens. Let me exchange the equation of state, but let me add some perturbations somehow. Guess what initial conditions I have for these perturbations and see what the dynamics happens. If I consider that, or let's say the more conventional way, and if there's differences. But this is still just preliminary thoughts that we didn't start.
Please.
Yeah, spinning this thought a little further, you mentioned, for instance, the production of heavy elements. I think the thing is that the region of the star that's actually affected by the phase transition is a relatively small fraction of the volume because it's just the innermost 5 kilometers. And then if we think about what's happening in the outer layers, I would guess one could get a first simple estimate by trying to see how the timescales change. Because in the outer layers, what's going to drive the nuclear reactions is still there's material that's going to be heated up and then cooling down again. And I guess the main effect here would be that because of the softening of the equation of... It's a softening of the equation of state, right?
Yeah.
That will somehow change the timescales over which the heating and cooling happens.
No, so I agree that maybe you don't change the spectrum of heavy element production, but I think you would change the velocity at which you eject the part of this because you're completely changing the channel, the energy pumping. That we measure multiple components and different velocities for multiple components in kilonova nowadays. It's an information you can access to. Yeah.
More questions, please?
So I wanted to ask about the viscosity. You said the wavelength of the perturbation is this, and therefore the viscosity is low.
Yeah.
So how exactly?
So within my estimations?
Yeah, exactly.
Yeah. So there, if you go to the paper, you have I didn't show it, but the corresponding size of these bubbles for that frequency of the order of 0.6 megahertz. It gives you something of the order of half kilometer. And again, the viscosity of QCD should really affect the result, or viscous effects should really come in if the size of these perturbations, or the typical gradient, is big enough, which would mean that I have variations of properties, or the wavelength of this perturbation is comparable to the femtometer. But here I'm in a regime in which I have a very, very long wavelength perturbation, so the viscosity wouldn't really act. It's a bit similar to the cosmological case, I think.
That's very encouraging, because also the viscosity in general in this kind of systems should determine the duration of your source. Do you agree? At least in this assumption of homogeneity and isotropic, and isotropy, what actually damps this kind of sound waves or turbulence is the viscosity of the system.
It is the viscosity, but the viscosity is going to have a scale set by the microscopic one. So if you compute the characteristic time that comes from this, it should give you something large compared to the...
Exactly.
Yes.
So I wonder whether this delta T that you put there shouldn't be maybe... we shouldn't. I mean, what I mean is that there is going to be also another time scale, which is the total duration of this sound propagation,
yes.
And this is going to be related to the femtometer.
Yes,
and
yes.
It will enter somehow this spectrum.
Yes. So yes, okay, I agree with you. I should compare this time scale of building up the signal with do these perturbations live as much as that? My naive guess would be yes, but of course I need to see that. There's also that I could start forming vorticity that kills all of this. And then I'm not familiar with the timescales, for example, in a known case like cosmological phase transition.
Vorticity would kill over all of this, but it would also produce gravitation.
It would also produce,
it's okay.
Yeah,
it's okay.
Yeah, but yes, exactly. Yeah. So yes, I should compute it, but I thought that the main two timescales that I was going to have to compare was the millisecond that could maybe capture that damping from the viscosity. Also, the could probably be of the order of the sound crossing time, and also with the fact that gravitational waves will escape faster. So I think that this would be the time scale that would be the shortest. I think that the viscosity damping would give me a larger time scale, but I might be completely wrong right now.
Yeah, so that really much depends. So how the light crossing time enters, it really much depends on whether the source can be assumed as stationary or whether it is coherent, etc. So yeah, it's something one needs to think about.
Okay, thanks for the comment. I missed that. Yeah.
Okay. Thank you, Juan.
Just a small comment. This efficiency factor 10 to the -2 that you have in the formula, of course, it's an estimate you made. I think numerical simulations would be needed to really capture that number. It could be much, much smaller.
Yeah, this was done as far as I remember. This was done in lattice hydrodynamic simulations. There was not finite density. I don't know if that would change this. This was overcooled bubbles. I don't know if that would change this. Yes,
you can get it analytically. That factor, it's possible.
By knowing the energy budget of a single bubble, you mean?
Yes, and by calculating by calculating the anisotropic stress. So I think it's a calculation which is doable.
Yes, if I have
Even
some equation of a
simulations.
state or some model for an equation of state, I could probably compute this analytically. Yes, indeed. I think that would be also connected to that I want to go further and for a specific model try to get the energy budget. So I could start making more accurate estimations.
Okay, so I think let's thank Mikel again.